Now let's understand few more concepts about the PV module. Okay, before you get into designing or further understanding of the PV systems or PV modules, you must understand what are the behaviors of voltage and current supplied by the PV module, or what is the relationship between the voltage and current supplied by the PV module. Okay, now let's assume we have a PV module, it's placed in the open space and it is receiving sun power. Okay, so there is sun and sunlight is being received by the PV module. Okay, now this PV module has two terminals which are available through a cable underneath, and both of them can be connected to a load. Let's for a moment assume that this PV module is not connected to any load. So this positive terminal and this negative terminal, if connected to a voltmeter, okay, let's connect it. Let's connect the negative lead to the negative terminal of the PV module and the positive lead to the positive terminal of the PV module. Then this PV module shall give you a reading on this voltmeter. Let's assume it's giving a reading of 45 volts. Okay, we will call this 45 volts at voltage open circuit. Open circuit means that there's no circuit and there's no load, and we're just measuring the voltage over the terminals or across the terminals of a PV module, and assuming it is giving right now at 45 volts on a particular time of the day. Okay, now let's connect a load to this PV module. Okay, now this is positive and negative terminals of the PV module. Assume we have a load which is a bulb, and we further assume that the power being supplied to this bulb can be controlled through an associated control or a device which has a knob over it. Okay, and we can rotate. Okay, we can rotate this way to control the supply to the bulb. Okay, now assume that we are also measuring the current through this circuit, and we will place an ampere meter over here. Remember, the ampere meter is always placed in series within the cable. So this is the terminals of the ampere meter, excuse me, and we will connect over here like this. Okay, now this negative shall be connected to this control device, and this is connected to the bulb. Okay, at the same time we are also measuring through a voltmeter, okay, the voltage across the terminals of the PV module. Okay, let's connect over here and let's connect over this. Okay, now we have voltmeter, we have ampere meter, we are measuring the voltage and ampere. Okay, and what we will do is we will start rotating this knob towards the right side so that we can start supplying power to the bulb. Once we start rotating, assume it has 10 steps. This knob has 10 steps. Okay, and we first rotate it first step out of 10 steps, and while doing this the bulb will start glowing on, and at the same time we are recording the values of voltage and ampere. Okay, and we have a table over here. So what we will do is that these are the steps of the knob. Okay, 1 2 3 4, this and 10 steps. Okay, this is the voltage and this is the current we are measuring. Okay, now at the step 1 it's possible. Okay, at step 1, before that there is step 0. Step 0 means it is off and no power is being supplied, and step 0 we can consider as there is no circuit. Okay, and the voltage open circuit, if you remember, was 45 volts in our previous slide. Okay, now at step 1, once we start giving power to the bulb, assume the voltage is, let's say, 43 volts and the current is 5 amperes. Okay, now let's rotate more this knob towards the next step, and that is step 2. Okay, now once we are at step 2, assume the voltage measured is 42 and the current measured is 10 amperes. Similarly, we will keep rotating this knob towards the step 10 and we will measure the ampere and current. Okay, Let's assume that at step 3 it is 40 volts and the current is 15 ampere. At step 4 we are at 38 volts and we have 20 amperes. Okay, and assuming that at step number 8, okay, we have 35 volts and we have amperes, let's say 14 amperes. Okay, assuming that this PV module can supply maximum 15 amperes. Okay, now at step 10 we can assume that the voltage measured was, let's say, 5 volts or maybe 0 volts and the amperes were 15 amperes. Okay, now we have to draw a graph between voltage and current depending upon or taking these values. Okay, now at 43 volts, so if this is 0, this is the graph for voltage, which is x-axis, and this is the y-axis for the current. Okay, and assuming this is from 0 to 45. Okay, and on the y-axis we have from 0 to 15 amperes. Okay, now if we draw a graph between voltage and current to show the relationship between them. Okay, at 43, the step 1, 43 is approximately could be here, and current is 5 amperes. So from the y-axis, probably this is 5 amperes. Okay, so this means this will cross over here, approximately here. Okay, so this is the step 1. Similarly, we will draw points for the other steps. So what will happen that the graph will look like this one, meaning that the relationship between the voltage and current is represented through this graph. In other words, if you want to know that if there is a voltage across the PV module and how much current shall be supplying, this can be found out from this graph. Suppose if the voltage across the PV module is 35, okay, then the current shall be 14 amperes. So this is how this shows that the relationship between the voltage and current of the PV modules. But now this graph has two parts. Okay, that means the relationship between the voltage and current have two parts. The first part is this one and the second part is this one. What this means? This means that the relationship between voltage and current from this point up to this point, okay, is reverse, meaning if the voltage is decreasing or if the current is increasing, the voltage is decreasing. So the relationship between current and voltage is reverse. Okay, this equation means that if the current increases, the voltage decreases. Okay, and this is what we have measured, and this is how the relationship between the voltage and current of the PV module works. Okay, in other words, if the load increases or the current increases, the voltage across the terminals will decrease. Now this relationship between the voltage and current of a PV module is up to certain limit. The reason is that every PV module has certain limit of supplying maximum current or supplying power to the load. Assuming that at this point, okay, assume that the voltage here is, let's say, 40 volts and the current is, let's say, is 14.5 ampere. Okay, now beyond this operating point, in other words, when the voltage is 40 volts and the current being supplied is 14.5 amperes, the remaining capacity left with the PV module to supply more current is minimum. In other words, if we increase the load or if we try to increase the current towards the load, the current will not increase. And this relationship is given by this graph, this portion of the graph. Meaning, suppose if we further try to increase the current beyond 14.5 ampere, the current will not much increase because the maximum capacity, let's assume, is 15 ampere. So it will increase from 14.5 to maximum by 15 ampere. However, we can see the voltage at the terminals of the PV module is reducing. Okay, so let's assume we are at this point. This point means the supplied current is close to the 15 ampere, but the voltage may be, let's say, 25 volts. And this is the characteristics of the PV module. So in this graph, the relationship between voltage and current can be divided into two portions. This portion, you can say, is more active portion, or okay, more dominant, while this portion, okay, is dormant portion, where the relationship between voltage and current is not reverse or direct relationship. If we try to increase the current, if we try to increase the load, however, the PV module is not supplying so much current, but the voltage at the terminals of the PV module is decreasing fast. So within just range of 14.5 to 15 ampere, we can see that the voltage has dropped from 14 to 0 volts. Okay, so that's how the PV module behaves in two different areas. Now the question is, at what point the PV module should be forced to operate so we can extract maximum power out of it. Okay, now if you remember, we made a table, okay, voltage, current, and there were steps, okay, 1 2 3 4, and voltage was here, current, 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 current. Now the standard formula of power is P is equal to VI. Okay, if we multiply voltage with the current, this will give us the power being supplied by the PV module. And if we multiply on the fourth column, we calculate P V into I, meaning multiply voltage with current, these two parameters, and write the answer here. This will give us the power being supplied by the PV module. Okay, so once the values are received for the power for each step, we can draw a graph. Okay, now this, if we draw the graph, let's suppose we have another axis here of the power, and let's say the values of the power ranges from 0 to 600 watts. Okay, and if we draw the graph based on these values, the graph will appear similar to this one. Okay, so this graph which we have drawn just now will be based on these values we calculate, that is the power calculated from multiplying voltage with the current. Okay, now this is the power graph, or the power being supplied by the PV module. Okay, now this graph shows that there is a maximum operating point with respect to voltage and current, meaning that there would be a operating point which is this one, which has got the maximum value out of these values calculated in this table. Okay, and this is called maximum power point, meaning this is the point where when voltage multiplied with current will give the maximum value out of all or the complete range of the PV module. So this point, which is actually corresponds to this point, is basically called the maximum power point on the voltage and current graph, and for the power graph it is this point. Okay, now we summarize all this discussion we have just gone through. We can say that the characteristics of the PV module, or the characteristics of the combination or the relationship of the voltage and current of a PV module, is such that at only one point this gives the maximum power. Okay, this means that at this point, when the voltage is, assuming it is 35, and the current is assuming is 14.5 ampere, this will be giving the maximum power. So we must try to operate the PV module at this operating point, and this point is called maximum power point. Okay, and nowadays the inverters manufactured are such that there is internal algorithm running within the inverter which forces the PV modules, or which operates the PV modules at this point, so that the maximum power is extracted from the PV module. Okay, that means the PV module is never operated over this point. This is a voltage, open circuit voltage, and obviously this is the point where the current is zero, and this point obviously the voltage is zero. So the PV module shall be operating over this point, which is MPP point, maximum power point, and the inverter which has these characteristics or which has this feature to operate the PV module at this point have a particular algorithm or equipment or devices inside it, okay, which is called MPPT, maximum power point tracking, meaning they are always running an algorithm inside the inverter to operate the PV module on this point to maximize the power supply. Now the relationship between the voltage and current we have just discussed might change in case the solar energy changes. Okay, the relationship we discussed between voltage and current and the graph we have just seen, it was this one when the solar energy assumed was 1000 watt meter per square. Remember, we discussed previously this voltage and current, assuming, though we did not discuss or did not point out that the sun energy was 1000 watt meter per square. But remember that whenever we are doing discussions, it is under standard conditions. The standard condition is standard test conditions, and standard test condition is that the sun energy being received is 1000 watt per meter square. However, in reality, the sun energy, you know it, we have discussed that it may not be 1000 watt meter per square. It may be less than 1000 watt meter per square. So in that case, what shall happen to the characteristics of the voltage and current relationship? Okay, and we can see here that it has got different graph. Okay, now if the sun energy is 800 watt meter per square, in that case, this graph shall be the relationship. This graph shall define the relationship between the voltage and current. Meaning, in the previous case, we assumed this was 15 amperes, okay? And this voltage open circuit was 45 volts, okay? Now, if the sun energy is 800 watt per meter square at particular time of the day or the time of the year, in that case, this graph is in relationship, meaning the maximum current at that time possible to be supplied by the PV module could be, let's assume this is 13 ampere, okay? So this value is 13 ampere. So it can't go beyond that. So in this case, the basic relationship is same. The only difference is that the maximum ampere being supplied by the PV module has reduced to 13 amperes. Similarly, for if the solar energy is 600 watt per meter square, we can see that the graph is shifting down, or let's assume that this may be, for example, it may be 11 amperes or 9 amperes or 10 amperes. So the at 600 watt per meter square of sun energy, the maximum possible current to be supplied by the PV module could be 11 amperes or whatever we the relationship is defined by the manufacturer. Now, if we look into the our maximum power points, okay, this point for all these graphs, meaning that when the sun energy is different, we can see that the maximum current possible to be supplied by the PV module is changing drastically. For example, this may be 14.5 or 14 amperes. This point could be 13 or 13.5 amperes. This could be like 11, 10 or 9 amperes, okay? But the change in voltage, okay, is not much. So from here we can conclude that when the sun energy changes or when it reduces, the voltage available at the terminals of the PV module doesn't change much. This is possible. Suppose that when the sun is 1000 watt per meter square, this operating point, the voltage is assuming it's 40 volts, okay? And when the sun energy is 400 watt per meter square, the voltage could be maybe 37 or 36, okay? So here we can conclude that the due to the change of the sun energy, the current capacity of the PV module changes, but the voltage at the terminals of the PV module doesn't change. And this can be related to the power also, V into I, okay? Once, because the voltage is not changing much, however, I is changing, so the power is changing. When I reduces, the power reduces. So this comes to the conclusion that the power being supplied by the PV module will reduce when the sun energy reduces. Now, before I conclude this presentation or session, one more thing I would like to add here is about the temperature coefficients of the PV module. Now, this data shown over here is taken from the same data sheet which we discussed moments ago in regard to while calculating power under different sun energy conditions. We took the rated power and dimensions. Similarly, these temperature coefficients are taken from the same data sheets of the Canadian Solar. Okay, now the temperature coefficients basically define the relationship between the given parameter and temperature. For example, this one, temperature coefficient P max, okay? Now this is minus 0.34% per degree centigrade. Now this parameter has minus sign. Minus sign means that the parameter shall decrease. Now how much? It is 0.34% against per degree centigrade, meaning that for each increase, okay, for each increase in degree centigrade or the temperature of the PV module, the rated power of the PV module shall decrease. This is minus, so we will say it shall decrease. How much? It shall decrease by 0.34%. Okay, so now let's assume the rated power is 640 watts, okay, in the data sheet, in the same data sheet we discussed. Now remember that always this data given in the data sheet is as per the STC condition, meaning that the rated power given by the manufacturer is only applicable if there is STC condition, or in other words, sun energy being received is 1000 watt per meter square and module temperature is 25 degrees centigrade. If any of these parameter changes, okay, the rated power will change. The PV module shall not supply power as given in the data sheet. Now for a moment assume that the sun energy remains constant 1000 watt per meter square, but the module temperature is increasing, okay. Assume that the module temperature increases to 45 degrees centigrade, so there is a change of 20 degrees centigrade, okay. Now the question is how much power shall be reducing. Okay, writing again here this parameter minus 0.34% per degree centigrade. Now minus is basically for just to indicate that this parameter or the power parameter shall decrease, okay. So we can remove this, okay. Now let's calculate how much in percentage the rated power shall decrease if the temperature of the PV module increases by 20 degrees centigrade. So we will simply multiply 0.34 by 20 and this comes out to be 6.8%. Okay, so the change in temperature of the PV module is 20 degrees centigrade, and as per this coefficient we took 0.34% and multiplied it with 20. It comes out to be 68%, meaning that the rated power, okay, 640 watts will change by 6.8%. so if we multiply 640 with 6.8%, this is approximately 43 watts, okay. In other words, if the temperature increases to 45 degrees centigrade, there is a change of 20 degrees centigrade in the temperature of the PV module, okay, the rated power shall not remain 640 watts as specified by the manufacturer. The manufacturer is saying that use this temperature coefficient, this one, and find the rated power. So the rated power of the PV module has decreased by 43 watt. In other words, if we subtract 640 from 43, this is approximately 600 watts. So the change in 20 degrees centigrade has brought the rated power of the PV module to 600 watts. So in our calculations, we shall be using 600 watts, and that shall be very much fair value in our calculation to be used to, in case you want to conclude the rated power or some other thing, okay. Similarly, the temperature coefficient for the voltage open circuit is also given. This means it is also negative sign, okay. This means that the voltage open circuit shall decrease by 0.26% for every increase in degree centigrade of temperature of the PV module, and this can also be found out in a similar fashion we have just done for the power.